Leaders and followers. Each node that stores a copy of the database is called replica. With multiple replicas, a question inevitably arises. How do we ensure that all the databases ends up on all the replicas? Every write to the databases needs to be processed by every replica. Otherwise, the replicas will no longer contain the same data. The most common solution for this is called leaders-based replication, also known as active-passive or multi-slave replication, and is illustrated in Figure 5.1. It works as follows. One of the replicas is designated to leaders, also known as master or primary. When clients want to write to a database, they must send a request to the leaders, which first write the new data to its local storage. The other replicas are known as followers. Read replicas as slaves secondaries to the hot standbys. Whenever the leaders write new data to its local storage, it also sends the data changes to all of its followers as part of the replication log or change streams. Each follower takes the log from the leader and updates its local copy of the database accordingly by applying all writes in the same order as they were processed on the leader. 3. When a client wants to read from a database, it can query either the leader or any of the followers. However, writes are only accepted on the leader. The followers are read only from the client point of view. This mode of replication is built-in feature for many relational databases, such as PostgreSQL, since version 9.0, MySQL, Oracle DataGuard, and SQL Server, always on availability groups. It is also used in some non-relational databases, including MongoDB, RethinkDB, and Espresso. Finally, leaders-based replication is not restricted to only databases. Distributed message brokers such as Kafka and RabbitMQ high-available queues also use it. Some network file systems and replicated block service devices such as DRBD are similar. Synchronous versus asynchronous replication. An important detail of a replicated system is whether the replication happens synchronously and asynchronously. In relational databases, this is often a configurable option. Other systems are often hard-coded to be either one or the other. Think about what happened in Figure 5.1, where the user of a website updates their profile image. At some point in time, the client sends the update request to the leader. Shortly afterward, it is received by the leader. At some point, the leader forwards the data change to the follower. Eventually, the leader notifies the client that the update was successful. Figure 5.2 shows the communication between various components of the system: the user's client, the leader, and two followers. Time flows from left to right. A request or response message is shown as thick arrow. In the example of figure 5.2, the replication to follower 1 is synchronous. The leader waits until forever 1 has confirmed that it received the write before reporting success to the user, and before making the write visible to other clients. The replication to follower 2 is asynchronous. The leader sends the message but doesn't wait for a response from the follower. The diagram shows that there is a substantial delay before follower 2 processes the message. Normally, replication is quite fast. Most database systems apply changes to follower in less than a second. However, there is no guarantee on how long it might take. There are circumstances when follower might fall behind the leader by several minutes or more. For example, if a follower is recovering from a failure, if the system is operating near maximum capacity, or if there are network problems between the nodes. The advantage of synchronous replication is that the follower is guaranteed to have an up-to-date copy of the data that is consistent with the leader. If the leader suddenly fails, we can be sure that the data is still available on the follower. The disadvantage is that if the synchronous follower doesn't respond because it has crashed or there is a network fault or for any other reason, the writes cannot be processed. The leader must block all writes and wait until synchronous replica is available again. For that reason, it's impractical for all followers to be synchronous. Any one node outage would cause the whole system to green to a halt. In practice, if you enable synchronous replication on a database, it usually means that one of the followers is asynchronous and the others are asynchronous. If the synchronous follower becomes unavailable or slow, one of the asynchronous followers is made synchronous. This guarantees that you have an up-to-date copy of the data on at least two nodes, the leaders and one synchronous follower. This configuration is sometimes also called semi-synchronous. Often, leaders-based replication is configured to be completely asynchronous. In this case, if the leader fails and is not recoverable, any writes that have not yet been replicated to followers are lost. This means that a write is not guaranteed to be durable even if it has been confirmed to the client. However, a fully asynchronous configuration has the advantages that the leader can continue processing writes even if all of its followers have fallen behind. Weakening durability may sound like a bad trade-off, but asynchronous replications is nevertheless widely used, especially if there are many followers or if they are geographically distributed. We will return to this issue in problems with replication lag on page 161. Research on replication. It can be a serious problem for asynchronous replicated system to lose data if the leaders fail. So researchers have continued investigating replication methods that do not lose data but still provide good performance and availability. For example, chain replication is a variant of synchronous replication that has been successfully implemented in a few systems such as Microsoft Azure Storage. There is a strong connection between consistency of replication and consensus, getting server nodes to agree on a value. And we will explore this area of theory in more details in chapter 9. In this chapter, we will concentrate on the simpler forms of replication that are most commonly used in databases in practice. Setting up the new followers. From time to time, you need to set up a new follower, perhaps to increase the number of replicas or the replace fails nodes. How do you ensure that the new followers has an accurate copy of the leader's data? Simply copying data files from one node to another is typically not sufficient. Clients are constantly raiding the database, and the data is always in flux. So, a standard file copy will see different part of the database at different point in time. The result might not make any sense. You could make the files on disk consistent by locking the database, making it unavailable for write. But that would go against our goal of high availability. Fortunately, setting up a follower can usually be done without downtime. Conceptually, the process looks like this. 1. Take a consistent snapshot of the leader database at some point in time, if possible, without taking a log of the entire database. Most databases have this feature as it's also required for backups. In some cases, third-party tools are needed such as InnoBackups for MySQL. Copy the snapshot to the new followers node. The followers connect to the leaders and request all the data changes that happened since the snapshot was taken. This requires that the snapshot is associated with an exact position in the leader's replication log. That position has various names, for example, PostgreSQL call in the log sequence number and MySQL call is in the bin log coordinates. When the followers has processes, the backlog of data changes since the snapshot. We say it has caught up. It can now continue to process data changes from the leaders as they happen. The practical step of setting up a follower varies significantly by the database. In some systems, the process is fully automated, whereas in other, it can be a somewhat arcane, multiple-step workflow that needs to be manually performed by an administrator. Handling node outages. Any node in the system can go down, perhaps unexpectedly due to a fault, but just as likely due to planned maintenance, for example, rebooting a machine to install a kernel security patch. Being able to reboot individual nodes without downtime is a big advantage for operation and maintenance. Thus, our goal is to keep the system as a whole running despite individual node failures and to keep the impact of a node outage as small as possible. How do you achieve high availability with leader-based replications? Follower failure, catch-up recovery. On its local disk, each follower keeps a log of the data changes it has received from the leaders. If a follower crashes and is restarted, or if the network between the leaders and the followers is temporarily interrupted, the follower can recover quite easily from its log. It knows the last transaction that was processed before the fault occurred. Thus, the follower can connect to the leader and request all the data changes that occur during the time when the follower was disconnected. When it has applied these changes, it has called up the leader and can continue receiving a stream of data changes as before. Leader failures failover. Handling a failure of the leader is trickier. One of the followers needs to be promoted to be the new leader. Clients need to be reconfigured to send their rights to the new leader, and the other followers need to start consuming data changes from the new leader. This process is called failover. Failover can happen manually. An administrator is notified that the leader has failed and take the necessary step to make a new leader, or automatically an automatic failover process usually consists of the following steps. 1. Determining the leader has failed. There are many things that could potentially go wrong: crashes, power outages, network issues, and more. There is no foolproof way of detecting what has gone wrong, so most systems simply use a timeout. Node frequently bounces message back and forth between each node. And if a node doesn't respond for some period of time, say 30 seconds, it is assumed to be dead. If the leader is deliberately taken down or planned maintenance, this doesn't apply. Choosing a new leader. This could be done through an election process, where the leader is chosen by a majority of the remaining replicas, or a new leader could be appointed by a previously elected controller node. The best candidate for leadership is usually the replica with the most up-to-date data changes from the old leader to minimize any data loss. Getting all the nodes to agree on the new leader is a consensus problem. Discussed on Chapter 9. Reconfiguring the system to use the new leader. Clients now need to send the right request to the new leaders. We discussed this in request routing on page 240 of the all leaders come back. It might still believe that it's the leader not realizing that the other replica have forced to step down. The system needs to ensure that the old leader become a follower and recognize the new leader. Failover is fraught with things that can go wrong. If asynchronous replication is used, the new leader may not have received all the rights from the old leader before it failed. If the former leader rejoins the cluster after a new leader has been chosen, what should happen to those rights? The new leader may have received conflict rights in the meantime. The most common solution is for the old leader unreplicated rights to simply be discarded, which may violate clients' durability expectations. Discarding rights is especially dangerous if other storage systems outside of the database need to be coordinated with the database content. For example, in one incident at GitHub, an out-to-date MySQL follower was promoted to leaders. The database used an auto-incrementing counter to assign primary keys to new roles. But because the new leaders counter lag behind the old leaders, it is reused on primary keys that were previously assigned by the older leaders. These primary keys were also used in Redis store, so the reuse of primary keys resulted in an inconsistency between MySQL and Redis, which caused some private data to be disclosed to the wronged users. In certain fault scenarios, see Chapter A, it could happen that two nodes both believe that they are the leaders. This situation is called split brain and is dangerous. If both leaders accept rights and there is no process for resolving conflicts, see multi-leader replication on page 168, data is likely to be lost or corrupt. As a safety crutch, some systems have a mechanism to shut down one node if two leaders are detected. However, If this mechanism is not carefully designed, you can end up with both nodes being shut down. What is the right timeout before the leader is declared dead? A longer timeout means a longer time to recovery in the case where the leaders fail. However, if the timeout is too short, there could be unnecessary failovers. For example, a temporary load spike could cause a node's response time to increase over the timeout, but a network glitch could cause delayed packets. If the system is already struggling with high load or network problems, unnecessary failover is likely to make the situation worse, not better. There are no easy solutions to these problems. For this reason, some operations teams prefer to perform failover manually, even if the software support automatically failover. This issue, no failures, unreliable network, and trade-off around replicate, consistency, durability, availability, and latency are in fact fundamental problems in distributed systems. In Chapter 8 and Chapter 9, we will discuss them in greater depth. Implementation of replication logs. How does leader-based replication works under the hood? Several different replications methods are used in practice, so let's look at each one briefly. Statements-based replication. In the simple case, the leader's logs, every write requests a statement that is executed and sends that statement log to its follower. For a relational database, this means that every insert, update, or delete, a statement is forwarded to followers, and each follower parse and execute that SQL statement as if it had been received from a client. Although this may sound reasonable, there are various ways in which this approach to replication can break down. Any statement that calls a non-deterministic function, such as now, to get the current date and time or rand to get a random number, is likely to generate a different value on each replica. If statements use an auto-incrementing column, or if they depend on the existing data in the database, they must be executed in exactly the same order on each replica, or else they may have a different effect. This can be limiting when there are multiple concurrently executing transactions. Statements that have side effects, triggers, stored procedures, user-defined functions, may result in different side effects occurring on each replica, unless the side effects are absolutely deterministic. It is possible to work around those issues. For example, the leader can replace any non-deterministic function calls with a fixed return value when the statement is logged so that the followers all get the same value. However, because there are so many edge cases, other replication methods are now generally preferred. Statement-based replication was used in MySQL before version 5.1. It is still sometimes used today and is quite compact. But by default, MySQL now switches to row-based replication. Discuss if there is another deterministic in a statement. VaultDB uses statement-based replication and makes it safe by requiring transactions to be deterministic. Write ahead log while chipping. In chapter 3, we discussed how storage engines represent data on disk, and we found that usually every write is appended to a log. In the case of a log structured storage engine, see SSL table and LSM trees on page 66, this log is the main place for storage. Log segments are compacted and garbage collected in the background. In the case of B3, see B3s on page 69, which overwrite individual disk blocks, every modification is first written to a write head log so that the index can be restored to a consistent state after a crash. In either case, the log is an append-only sequence of bytes containing a write to the database. We can use the exact same log to build replication on other nodes, besides writing the logs to disk. The leaders also send it across the network to its followers. When the followers process These logs, it builds a copy of the exact same data structures as found on the leader. This method of replication is used in PostgreSQL and Oracle, among others. The main disadvantage is that the logs describe the data on a very low level. A wall contains details of which bytes were changed in which disk blocks. This makes replications closely coupled to the storage engine. If the database changes its storage format from one version to another, it's typically not possible to run different versions of the database software on the leaders and the followers. That may seem like a minor implementation detail, but it can have a big operational impact. If the replication protocols allows the followers to use a newer software version than the leaders, you can perform a zero downtime upgrade of the database software by first upgrading the follower and then performing a failover to make one of the upgrade nodes the new leaders. If the replication protocol does not allow this version mismatch, as is often the case with while shipping, such upgrades require downtime. Logical row-based log replications. An alternative is to use different logs formats for replication and for the storage engine, which allow the replication log to be decoupled from the storage engine internals. This kind of replication log is called a logical log to distinguish from the storage engine physical data representation. A logical log for a relational database is usually a sequence of records describing writes to databases tables at the granularity of a row. For an inserted row, the log contains the new value of a column. For a deleted row, the log contains enough information to uniquely identify the row that was deleted. Typically, this will be the primary key. Or if there is no primary key on the table, the all values of all columns need to be logged. For an updated row, the log contains enough information to uniquely identify the updated row and the new values of all columns, or at least the new values of all columns that change. A transaction that modifies several rows generates several such log records, followed by a record indicating that the transaction was committed. MySQL bin log, when configured to use row-based replications, use this approach. Since a logical log is decoupled from the storage engine internals, it can more easily be kept backward compatibility, allowing the leaders and the followers to run different versions of the database software, or even different storage engines. A logical log format is also easier for external application to parse. This aspect is useful if you want to send the context of the database to an external system, such as data warehouse for line of line analysis, or for building custom indices and cache. This technique is also called change data capture, and we will return to it in chapter 11. Trigger-based replications. The replication approach described so far are implemented by the database system without involving any application code. In many cases, that's what you want. But there are some circumstances where more flexibility is needed. For example, if you want to only replicate a subset of the data or want to replicate from one kind of database to another, or if you need conflict resolution logic, the handler writes conflict in page 171, when you may need to move a replication up to the application layer. Some tools, such as Oracle Golden Gate, can make data changes available to an application by reading the database logs. An alternative is to use features that are available in many relational databases, trigger and store procedures. A trigger lets you register from custom application code that is automatically executed when a data changes. Write transactions occur in a database system that the trigger has the opportunity to log these changes into a separated table, from which it can be read by an external process. That external process can be applied any necessary replication logic and replicated the data changes to another system. Databooks for Oracle and Bucardo for Postgres work like this, for example. Trigger-based replication typically has greater overhead than other replication methods, and is more prone to bugs and limitations than the database built-in replication. However, it can nevertheless be useful due to its flexibility.